Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday I did sort of I guess it was impromptu because I didn't know we were going to go into it in quite so much depth, but I needed to explain some matrix math in order for people to understand sort of what I was doing and in a particular part of the code. And so I gave a pretty complete explanation actually of how 2D matrices work for geometric transforms and how the inverse and the transpose of them are related, and sort of a bunch of other stuff that you would need to know if you were doing 2D graphics work and needed to do some rather advanced, well, I guess not rather advanced. I'm going to use the phrase basic advanced stuff. You know, plenty of people write 2D games and things without really ever knowing anything about a matrix, but as soon as you want to do something fancy, you kind of need to know this stuff. It's not advanced per se, but it's more advanced than not knowing, I guess. Not sure how to say that any other way. So anyway, we've come to the point, hopefully if you watched the stream that we did that talked about that, now you know that the only thing we have left to do now is show how if we want to do a full inverse of a 2D matrix, a 2x2 matrix I should say, how do we do that? And I'm going to kind of show how that works today. And this is going to be not very much fun for me, certainly, because this is the kind of stuff I hate as far as doing math is concerned. Oops, gonna have to reboot my Milton there. Let's see here. There we go. Run. And so here we go on day 320 with inverting a 2x2 matrix. I was basically going to show how to do this from first principles, kind of, and it's just a lot of fussy math. We're doing only a 2x2 matrix, so it's as easy as possible, which is nice. It's, you know, a 1x1 matrix would just be a scalar, but, you know, it's still a bunch of fussy math terms. So I'm going to do it, and hopefully I won't make too many math mistakes along the way. Feel free to use a computer algebra package when you're actually doing stuff like this, but I kind of want to show how it works out just so people can see it once. All right, so if you remember from yesterday, what I said was, you know, we had an equation that looked like AP equals P prime, and we actually wanted to solve for P, so we needed to be able to multiply both sides with the inverse of this transform, A inverse, this guy right here. And so that's going to give us this equation. Now we know that A inverse A equals the identity matrix, right? So this goes away and we're just left with P equals A inverse P prime. And this is the equation, that's good. This is the equation we wanted to solve. And so in order to solve it, we obviously need to know how to produce A inverse. And so that is where we are at today. So what we want to do is say, well, if I had an A matrix, and let's say it's just A, B, C, D, like so. If I have an A matrix and I would like to produce the inverse of that A matrix, well, I've already kind of shown you everything you need to know to solve for what that actually is from first principles. If you want to just work out how to do a matrix inverse yourself, you actually know how to do it. And let me explain why, and then I'll show you how to do it that way. And then we can also see some kind of shortcut approaches that you can follow. But let's just take a look at this. So here's my A matrix. And what I said yesterday when we were just talking about what the definition of the inverse was and what the definition of the identity matrix was, we said some very basic things, which is just that A inverse times A has to equal the identity matrix, right? That's the definition of the inverse. That's what we know has to be true. And so if we have this equation, you'll notice that this is a matrix equation where we have a 2x2 matrix times another 2x2 matrix equaling a known quantity. Just, you know, the identity matrix is just a known quantity. It's that, right? And so if we take a look at what this is, well, this is a equation that has this is an equation that essentially has 4 scalar equations in it, right? Because a 2x2 matrix, so it's 4 scalar equations, right? One for each slot. matrix multiply. And we know all of the values in the A matrix. That's what we're given to start with. So we have 4 unknowns in the A inverse. We don't know what what those 4 elements of A inverse are. We have 4 knowns in the A, 4 knowns in the I. So we have 4 equations in 4 unknowns, essentially, as you'll see in a second, in case you don't believe me, which means we can just solve this, right? We can just solve it. It may be a lot of fussing, but we have what we need, right? So take a look at what ends up happening here. So I have an A inverse matrix. I don't know any of the values of this A inverse matrix, right? I have no idea what they are. So let's just say we have X, Y, Z, W are the terms of my inverse matrix, right? So this is my A inverse here. And then I've got my A matrix, right? And I'm going to make my A matrix kind of big because we're going to need room for our terms down here, right? And my A matrix, I just said, was A, B, C, D, okay? So what are all the terms of this product here, right? And I know, again, that this equals the identity matrix 1, 0, 0, 1, 0, right? There you go. So what are the terms? We know how to do matrix multiply. We've done it tons of times on Handmade Hero. So I've got AX plus CY in here. I've got AZ plus CW, right? I've got BX plus dy, and I've got bz plus dw, right? Those are my dot product terms, right? Ax, cy, az, cw, by, ooh, made a mistake there, by, glad I checked, by, dw, oh no, I didn't, no, that's nonsense. I did it right the first time. Bx, my cross was just a little bit off. Bx, dy, bz, dw. Okay? So I've produced all of the dot products. Like I said, matrix multiplication you could think of as just a series of dot products, every column with every row. And that's what we've got here. And so hopefully you can see now why I say we have 4 equations, because this is what we are left with, right? And obviously, if I'm saying that this matrix is equal to this matrix, then each of their elements must be equal. So I actually know that AX plus CY equals 1, right? I know they have to be equal. I know that BX plus DY has to equal 0. I know that AZ plus CW has to equal 0. And I know that BZ plus DW has to equal 1, right? So I know the A's, the B's, the C's, the D's, right? I know the 1s and 0s, so I have 4 equations and only 4 unknowns, x, y, z, w. So we can solve this equation strictly by back substituting, right? We can actually just go ahead and do it. Like I said, it's a pain in the butt, but here we go, right? Let's just do it, grin and bear it. And like I said, without needing to know any trickery or any special stuff about linear algebra, just from what I already had explained, you could have set this up and solved it, right? Because we know that that's what has to happen if we want to find the inverse matrix. So yeah, let's go ahead and I guess use the 0 guys first. Let's start with this equation here. We have bx plus dy equals 0. So it's trivial for us to solve this in terms of, let's say, the x variable, since, hey, let's solve for x first, why not? So we would know that that would be bx equals negative dy, right? Or x just equals dy over, x equals dy over b, right? Very, very straightforward. So now I can plug that in. I could plug that into this guy up here. I could say, okay, I now know what x is, so if I want to solve for y, well, I've got an equation in terms of y, an equation in terms of x, right? And you can see how I'm kind of doing this. I'm just saying, well, really, because these don't have any cross terms, I could think of it as, as being 2 equations, one in x and one in y. I'm sorry, 2 equations in x and y and 2 equations in z and w, because that's just how it happens to fall out, right? You're only going to have x and y's on this row. There won't be any x and y's in this row. So when I go to solve, I don't have to think about that, thankfully, right? All right. So I've got x equals negative dy over b, and then I can just plug it back into here where I'll have only y's, right? Because I'll have ax plus cy equals 1. Well, the x I now know what it is, so I can say a times negative dy over b, which is what I solved for before, plus cy, there we go, equals 1. Okay? And so now I should be able to actually solve for y. I would have negative a dy over b plus cy equals 1. You can see here that I can pull out the y term, right? I could pull out the y term here and just get c minus ad over b equals 1, right? And then I am left with just the actual answer for what y is, which is just y equals 1 over ad over b. Now, big caveat there, that's if I didn't make a math mistake. I'm awful at doing math by hand. So, you know, what I should say is it's something like c minus ad over b, modulo the math errors that Casey probably had along the way. But you can see now that you've got a equation in terms of y and all knowns on the other side, because these a, b, d, and c, those are all obviously pieces of those are all things that we knew from the original matrix, right? So yeah, so let me just quickly double check that, because like I said, I usually make math errors. We have bx plus dy, so I just subtracted the dy to the other side, like so, and then I divided by b, so that's where my x, I had ax plus cy. I substituted in my negative dy over b, so I had a negative dy over b plus cy equals 1 there, right? So that's negative ady over b plus cy. And then I just pulled my y out. I flipped the terms because this one's negative and this one's positive, so I put the c first and the negative 80 over b, and then I ended up with this term here, right? Now, it's worth noting that if I wanted to, I could sort of, I could write this as a combined fraction, or I could do a bunch of the things to this if I wanted to. Like, I guess what I'm saying is there's other ways I could phrase this, right? Because you know, it's a 1 over right now, but then there's a fraction on the bottom. So if I wanted to kind of simplify this term a little, I could do so, right? And let me just show you what I mean by that. So if and again, this is all caveat if I did the math right. 1 over this term right here, c minus ad over b, well, if I wanted to combine this fraction, right, I could multiply this guy by b over b, which is, you know, equal to 1, and I could get bc over b, right, minus ad over b, right? So I could turn that bottom into something that could actually be done as a fraction. So it would become bc minus ad all over b, right? I mean, that's just, all I'm doing is simplifying that bottom a little bit. Why did I do that? Because now that I've done that, 1 over something, right, I can just flip it. I can get rid of the 1 over now and just end up with, you know, b over bc minus ad, right? So that's really a simpler version of that term, b over bc minus ad. It's a cleaner version than this is, where I've got the 1 over there, right? So b over bc minus ad, if I did the math right, as I said before, I now know that that's the y element of my matrix. So here's my A inverse. I'm just going to rewrite it here with the one that we know, okay? So here it is down here, what I say it was, b over bc minus ad, right? So b over bc, bc minus ad, okay? All make sense? Okay. So let's just continue with the exact same process. Again, like I said, this is just a lot of like high school algebra homework. I mean, at some level, you could say this was junior high school algebra homework, right? Where in pre-algebra, where they just made you like move terms around for no reason, which honestly is what most of math is before you get to college, I suppose. So anyway, we still have this equation here, x equals negative dy over b, or rather, I should say, we have this equation here, bx plus dy. We can plug in our equation for y to solve for x now, because we do know that bx, right, plus d times this, right, which would be db over bc minus ad, right, is going to equal 0, And that's all in terms of x as well. So if you take a look at what happens there, we would have bx equals db over bc minus ad negated, right? I'm moving this to the other side. And then I would be dividing by b, right? So I'd have x equals negative, and you'll notice there's a b on top, and I'm dividing by a b, so those go away, and I'd just be left with d over bc minus ad, right? So negative d bc minus ad. Now you'll notice something interesting about that. Again, I always have to caveat to the math right. I am not strong with manual computation. But you can see our x, negative d over bc minus ad, that's really kind of similar, right? You can kind of see that that's a pretty similar term here, right? bc minus ad. It's got the same denominator, right? Which is kind of surprising a little bit, right? I mean, it just seems a little odd. So even with my shoddy math skills, we're starting to get something that looks like it has a little bit of structure here, so maybe that should give us some encouragement. But I'm just saying keep an eye on that, right? All right, so now let's do the exact same thing with these equations. Now, those of you who are particularly good at math will probably note that we can probably shortcut this a little bit, because if you look at what these look like, right, you can see that they're essentially the same equations, almost, except the the AC terms are the ones that equal 1 here, and the BD terms are the ones that equal 0, whereas in this one, it's the same equations, but the 0 and the 1 are flipped, right? So essentially, we could just substitute, we could flip the AB and the CD, right? And the solutions to the equations would be the same. Do you see what I'm saying? Because it's really just the same two equations with z in place of x, w in place of y, right? And the 0 and the 1 flipped. Make sense? So we could, if we were so inclined, jump right to the conclusion that we're going to get the same two terms here, but with the opposite set of letters. But I'm going to do it out longhand just so you can see it. Like I said, we should do this once. I think it's important to just kind of see everything out once before you start to do those little swizzles and stuff. So anyway, do the same thing I did before. Going to start with a 0 term. So I've got an AZ plus CW equals 0, right? I want to solve for one of these, and so I'll just start solve for the z, right? So I'll have AZ equals negative CW, or z equals negative CW over A, okay? So that's my temporary term for z. Again, it's in terms of w, so I haven't solved for z yet. I've just put it in terms of w. But now I can do the same thing I did before, which is my back substitution, right? I can take bz plus dw, and I can substitute it in there, right? So I've got bz plus dw, and that's going to equal 1, right? bz plus dw equals 1. And so now I can substitute in my z term. So what I've got here is I've got b times my negative cw over a, right? That's my z term, plus dw equals 1. Well, now I've got it such that it's all in terms of w, so again, same exact process coming through. So I've got negative bcw over a plus dw equals 1. Again, I want to solve for w, so I'm just going to pull the w term out. I end up with the d minus bc over a equals 1. Again, like I said, very similar equations because we've just kind of reversed some terms around, but it's basically the exact same system, so it's no surprise, right, that it looks exactly like this guy here, only with some of the letters changed around, right? So again, I can finish solving for w. I would get 1 over d minus bc over a. There's my inverted term, right? And like I said before, we want to try and simplify this down so that we can see the structure in the equation. So I'm going to continue doing exactly what I was doing before to get this into the simplest possible form. Again, multiply by a over a so that I can combine these two fractions. Well, this guy isn't really a fraction, right? But you get my point. So I'd have ad over a minus bc over a. That allows me to combine the terms. So that would just give me 1 over ad minus bc over a, right? And then I can finish the sort of uninversion of the I don't know what you want to call it. I can finish the d version. of this by flipping the fraction around, just flipping it over, and getting AD minus BC on the bottom and A on the top, right? So I have A with AD minus BC there, so let's see here, where am I at? Yeah, so A over AD minus BC, and that was my, what was the term I was solving for? That was my W, A over AD minus BC, right? So there's my W, A over AD minus BC, right? And, you know, just pay attention to this. Again, like I said, you can see a lot of structure there, but it's not quite the same bottom turn, right? But, you know, don't worry about that too much because we're going to get to looking at the structure of this in a second, but just I was saying, like, look at the similarity a little bit there. So now we've got our W term, so let's go back up to the equation that we didn't use, right, that not that we didn't use, but that we used as our starter. I should be circling this one. That we used as our starter here, right, where we see the AZ minus CW. So if I start with AZ minus CW again, AZ minus CW, and now I substitute in my W, I will be able to solve for Z for reals this time. AZ minus CA over AD minus BC, right? And that equals, I lost it again, it equals 0, right? Okay. So if I want to finish solving for this guy, I know I have to solve for my Z. Well, that doesn't look particularly hard. I'll just end up with AZ and CA minus, I'm sorry, over AD minus BC here, right? So I just need to divide by my A, but of course there already is an A. So I end up with just C over AD minus BC, right? And that's it. So C over AD minus BC, C over AD minus BC, right? And there's all my terms. Now, what you'll notice about these guys is if I wanted to, I'm pretty sure I have a math error in here somewhere because I'm expecting this to be slightly more symmetric with the minus. So I think I missed A minus, which, let's be honest, is pretty good for me. Like I said, very, very bad at symbolic math manually. I always do stuff like that, which is why I hate doing it, right? I really want the algebraic Blackboard program, even for when I'm working stuff out myself, where I just tell it what math operations I want to do and it did it. I don't know why that program doesn't exist. I've always thought I should just write it, but it doesn't. Because I usually don't actually want it to solve stuff for me, because a lot of times I'm working with things symbolically that it can't solve necessarily, and I just want to be able to manipulate the terms with predictability and know that I don't make a careless error. I really wish I had that. Anyway, but point being, you can look at the structure of this, and I'm going to check the math in a second, but even at this point, you can see that actually all of these have the exact same divisor, minus the fact that some of them are negative. Because if I wanted to, I could turn this into the same divisor just by negating this term, right? If I have C over AD minus BC, right, and I want that to look like C over BC minus AD, all I have to do is multiply it by -1 over -1, which is, right? That's equal to 1. If I multiply that, I would just get negative C over negative AD minus BC, which is BC minus AD, right? So I can produce this just by doing that. I can regularize it so that it has the same bottom as the rest of these guys. So I'm going to go see if I can just quickly find my math error, because we're so close. Almost had an error-free run. You might as well go for broke, right? I mean, come on. So let's see here. Where was I at? So let's see. We've got... well, you know what? Actually, here's the easiest way to do it, I suppose. If I was to convert these all to the same one, let's convert them all to AD minus BC, right? So what I would end up with in that case is I would end up with a matrix that would look like D over AD minus BC, B, negative B, over AD minus BC, right? And then I would end up with C over AD minus BC and A over AD minus BC, right? So if I take that, I should be able to multiply it, if I want to, by my original matrix, and I should be able to get the identity, right, if I'd done it correctly, right? A, B, C, D. And I think I have a sign error, so I think this should show us pretty quickly which pair of terms is right and wrong, or at least get us close to that, right? So let's take a look. So say I'm going to multiply this down, right? Well, they're going to have the same divisor, so I'd end up with AD, right, plus BC over AD minus BC, right? That's what I would end up with. And you can see that this is slightly wrong. That should be a negative there in order to make this equal 1, right? So it looks like this term is probably incorrect. I probably missed the minus, as I suggested, right? If that makes sense. The next one, this would give me negative BA, right, plus AB, and that's perfect, right? AD minus BC. That's AB minus AB, that's 0, which is exactly what I wanted, right? So those two terms look correct, right? So these guys look good. We know this guy's wrong, so we can just ignore that for a second here. And then let's double check this guy. So if we have CD times this, we would get negative BC plus DA equals AD minus BC. And hey, look, that's exactly what that is, so that's 1. So I think we know that these terms are correct, and we just don't know about these terms here, but it looks like this guy is our error. And hey, that was, I think, the guy that I did last, so I guess I just ran out of steam. Right, this was that guy right there. So let's take a look. I had AZ minus CW equals 0. Is that correct? AZ, well, that would do it. Looks like you just copied it down wrong. Can't fault myself too much for that, jumping all over the blackboard here. So it's really a plus, AZ plus CW. So if we fix that bug, we get AZ plus CA. A must be right. When this transfers to the other side, it becomes the minus, and that's where we lost our minus. That's not too bad. I won't be too hard on myself for that. But that tells us what we needed to know. And now we have finished inverting our matrix. So we actually have our matrix here, and we can write this actually in a pretty compact way if we want to. We could really just say this is 1 over AD minus BC, and the elements are just D, negative B, negative C, A, right? So this right here is our A inverse. If our A is equal to A, B, C, D, okay? That's what we've got. And we just proved that it worked because we multiplied it out and got the identity matrix, so everyone's happy, happy birthday, everything's great, right? Well, what we can look at when we see this is you can see very quickly now that if you just wanted to remember in your head how to invert a 2D matrix, it's actually pretty easy to remember. This guy right here has a special name that we won't go into too much detail, but this is the determinant. This guy right here. Well, actually, that guy. And the determinant of a matrix, of a 2D matrix, is just the product of the diagonal minus the product of the counter diagonal, right? So it's AD minus BC. So it's pretty easy to remember, again, if you just want to remember how to invert one without having to go through all that. It's pretty easy to remember. You take this diagonal, multiply it, and subtract this diagonal after multiplying it, and you get the determinant. 1 over that determinant, and then you just multiply by the matrix effectively flipped, like counter-transposed, right? Flipping it this way and negating the opposite diagonal, right? So that's one way you can think of kind of like mnemonically remember if you would like to, or you can just do it up by hand, or you can look it up, or you can do whatever you want. But point being, now you can see where that comes from, right? Anyway, so that's what we've got. And hey, let's take a look at what actually happens with this matrix if we want to use it for the purpose that we said we wanted to use it for, which is computing the UV coordinates, right? Before, we were doing a transpose. So let's actually look at what the difference is here, right? So before we did A transpose and we had our screen space P, right? And we were producing the U and V's, right? So before we were saying like, let's say we have X and Y. So let's say we're doing the vector XY, the screen space XY, right? That's our P. So before we were doing ATP to get our U and V's, right? That's how we were doing it. And what did that give us, right? Well, that just gives us the A transpose P, right? That just gives us, if the matrix looks like this, A, B, C, D, or whatever. And you know what? I guess, well, we'll fill in what the values actually are later, I suppose, because we know what this was the x-axis and this was the y-axis of our transform, right? But anyway, if we have A transpose P and we're doing this matrix, it'd be A, B, right, times xy, so it'd be AX plus BY in the top, and then we would end up with C and D for the bottom, right? CX plus DY. That would have been if we had not transposed it, I guess I should say. And so if we transpose it, we're going to flip those around. So we're going to flip the C and the B, but the A and D stay in the same place, right? So that would be AX plus CY, and for the bottom row, BD, right? So that's going to be BX plus DY. So that's what we were computing, right? If that makes sense. And to our credit, we did actually still try to divide by the length amount there. So we were doing compensation for the length of the x and y vectors, but that's all we were compensating for, right? And so the length of those vectors, we could look at again. We'll take a look at this. I guess we should probably go look at the code and put in exactly what we're doing. But let's actually just take a look at what happens when we use our determinant to do the actual inverted, the actual inverse operation here, right? So if we were going to do that, we would be multiplying by this matrix and then dividing by this value, right? So our final values that we would get would be dx minus by over AD minus BC, and then negative CX plus AY over AD minus BC, right? That's what we would actually get. All right. And if I wanted to flip this around just for good measure, right, you could imagine, I don't know, how do I erase here? Eraser E. I could actually do it the other way around and say AY CX, right, if I wanted to. But I'm not going to do that. I'm going to leave it in the opposite order. Okay. So this is the actual vector that we would get back. And if we look at what these are, we know what the A, B, C, and D are, right? Because our matrix was set up such that this was our UX, the U vector, right? Or the x-axis is x, right? XX. I don't know how we wanted to write it. Let's call it UX for now. And this was our UY, right? This was our VX, and this was our VY, right? So if I'm going to replace those, then what I get is on the bottom of these guys, my A is UX, right? My D is VY. So it's UX VY minus the BC, right? So VX UY. Or I guess we could write it UY VX, right? So it's UV, it's like the, it's the XY YX, right? Okay. So same thing would be up here, VY minus UY VX, exact same product. And then on top, we would just have our D term, which is VY times the input X coordinate minus our VX, right, times the input Y coordinate. That's what we get up there. And for here, we would get negative UY times the input x coordinate plus vx times the input y coordinate. So that's the actual equation now for doing the reverse mapping that we actually wanted to do. And so if we go back to our code now, we can actually take a look and be in a position to, hopefully, fix our bug. So let's go ahead to Handmade code. That's in the renderer, and that's in, draw rectangle quickly. And in draw rectangle quickly, you can see where we're actually doing this code here. So here's where we're computing, excuse me, our u and our v coordinates, and we have to replace these computations with the correct ones. So let's go ahead and let me load the project file there. So let me go ahead and pop back here. And let's load up. Oh, we're already on it. There we go. And so you can see that the body is just doing, the totally wrong thing there, right? It's not like what the OpenGL one is doing at all. And so that's the bug that we're trying to fix. So if we come back here and look at what we were doing, well, we've got these sort of nx-axis stuff that's happening, right? And we were computing that up at the top here somewhere, nx-axis, there it is. So you can see here that we have 1 over the x-axis length squared there, and we are multiplying. So we're effectively going to divide by whatever the length of the x-axis is, in addition to doing the basic divide, which, I'll be honest, I'm not sure why we were doing. Let's take a look here. I'm not sure why we're doing it. Because we want to map it into the 1 to 0 space, right? So when we do that inverse transform there, we want to first compensate for however long the x-axis is, but then we also want to divide by the total length of the x-axis to convert our length back to be 0 to 1, right? So in actuality, there's nothing wrong with us having sort of done that part either. And I have to think for a second about whether what we need to do there for that. We didn't really handle that part in the previous one, did we? Because our A matrix, no, I guess we did. In theory, our A matrix should be taking that into account now, I believe, right? So I think we don't, in theory, if I'm not very much mistaken, and it's easy with this much stuff to be mistaken, I think we actually just can do this operation and be done, I believe, right? Yeah. So I think we don't really need any of this stuff anymore. I think we can just use the x-axis components and the y-axis components and do it. Now here's the interesting part. So what you can see here is the term that we actually care about here. We can turn this into essentially exactly what we were already doing, because you can see that we have this is our v term, right? This is the v output, and this is the u output that we were trying to get. So this term is constant. ux vy, uy vx, that's a constant. We can just compute that ahead of time and be done, right? Similarly, this at the top is just a dot product, right? It's just a dot product with the vector negative uy positive vx, and this one's the dot product with vy negative vx, right? Of the incoming x and y. So if we just do the exact same math we're already doing, but just prep our vectors slightly differently, we can actually just, I think we can just keep the code identical, right? because the nx axis is just needs to be prepped in this way, right? So first, let's compute that determinant, right? And that's going to be our x-axis x, right? So I'm just reading off this bottom term here. Our x-axis x times our y-axis y minus our x-axis y times our y-axis x, right? That's that determinant value that's under there. And now when we produce these matrices, we want to be very specific with these. We don't want to do that anymore. We want to do our specific equation. And our equation is, for the x-axis, it's going to be vy and minus vx, both of them over the determinant, right? And if this determinant happens to be 0, right, if the determinant equals 0, then that means that we've got a very degenerate, like we've sort of collapsed our things into the same place. So I feel like if the determinant gets too low, obviously we also we don't want to divide by 0. So we could just stuff an arbitrary value in there in that case. But we could also think about what that actually means a little bit later. Like to do Casey, just don't draw if the det is 0, is close to 0. Because it means it would be such a thin thing that you wouldn't be able to see it anyway, probably. But anyway, that's getting a little ahead of ourselves. All right, so that nx axis, again, like I said, it's vy, so that's the y-axis, y component, and it's over the determinant, obviously. And the other one is the v-axis x component. Sorry, the y-axis x component over the determinant. Yeah, and these, by the way, are not needed anymore. And then similarly down here, we would have, wait a second, we missed something here. It's vx, vy, let me read that again. Dx minus by. So d is v, and b is u, or is also v, never mind. This is a and c, so that should have been u and u. So these should have both been u, right? Right? I'm not hallucinating there, am I? I don't think I am. Yeah. Yeah. All right, so back to our original story. So that's going to be negative x-axis x over the determinant and x-axis y over the determinant. Okay. So now, barring lots of stupid errors that I may have just made, that is what we actually want to do. And then we are still computing the dot products here we're now just computing them with different things, right? We've just scaled and multiplied them differently, but we're still computing the exact same equations. There's really nothing else to it. So let's just see our first depressing result, because it'll probably not be right at all, and you can see that it's not. So we've got some work to do, obviously, there, but, like I said, nobody ever said it was going to be easy. All right. So we got a couple things to check. The first thing that I have to do is I have to make sure that I think through whether or not we need a squared scale in there, right? Like before, I was a little bit nervous about that because I was thinking about whether it should be squared or not. I think this should take care of it, though, because the determinant itself is effectively going to be doing basically a squaring kind of an operation there. So dividing by this, that seems like it should do it. So I'm not 100% sure that we would need anything else for computing those UV coordinates. In theory, it should do the reverse mapping so that it's in the 0 to 1 space. Excuse me. I believe, right? I believe. And so, yeah, these guys, I think, are what I would have expected us to dot with. Now, let me make sure that I'm not doing anything weird down here. I want to make sure that I'm computing the right thing. So we mul PS to get our U. We mul PS with the n-axis and the PYN. What is that? PYNX. So we do a mul, and then we do a mul. So that's all good, I think. This is Y. That looks right. That looks all good to me. All right. And again, sorry if I'm not talking as much as I should be. We're missing a minus. This is supposed to be minus. I copied it down wrong. There we go. I copied it from my Blackboard wrong. All right, so debugging this is going to be quite the pain. You know, the fact that we don't see anything yet suggests to me that we've got like a bad scaler or something, because we should at least see stuff that's kind of messed up, right? And so, you know, it feels like we're super far off, or maybe misremembering how these guys got used. But I'm pretty sure that we're okay there. Now, let me just make sure they're also not used in any other place, but I'm pretty sure they're not. Yeah, so these are only used for that process, right? So that's all good. And we're already subbed out the origin, so we're literally just taking these dot products here, and that's literally it. So before, what we were doing is we were taking, you know, the x-axis and we were normalizing it by dividing it by its length squared, and that's not that different from what we were doing here, to be honest, right? Because if you take a look at what that would have been, right, previously, effectively what we were doing is we were saying, well, okay, previously we're going to take x-axis x squared plus x-axis y squared, right, and dividing, you know, each one by its respective one of those, right? That's what we were sort of saying we were going to do. And so I don't really know why we wouldn't get anything there. And I think I may want to go. I guess I could step through this. I'm just trying to think if the easier way to debug this will be for me to go back up into to the slow code and draw it there, if that makes sense, just to see. Well, I'm going to try stepping through it like this. So I'm just going to turn off optimizations for the moment. I'm going to go into this code, or try to anyway. Here it is. And I'm going to step into here. Now, hopefully we'll get somebody with just a normal x and y axis, one that's very simple. And we'll see, right? So there's the x-axis, there's the y-axis, and hey, they're perfectly, they're going in exactly the same direction, so that's nice. And yeah, and so hopefully that should give us something reasonable to work with. Let's see what the determinant was. There's the determinant. All right, and let's take a look at what our nx axis is. All right, so we're getting much too tiny, is what I would say. At least it looks much too tiny, although it's hard to say. I mean, I guess with 1,000, yeah, no, it looks like it's maybe 10x off there. Yeah, it's hard to say. But yeah, so thinking it through, like, it would be nice if we just had a slightly easier, one that was a little bit more normalized, I suppose, but, you know, even as it goes, if we take a look at what the n-x-axis values are, when we dot product with this, it's going to be moving basically that slowly, right? So it's going to be a, you know, if that was 100 pixels, let's say, to go the whole length, it's actually a little bit more than that. So if you look at what that's doing, that's pretty close to what I would have expected, actually. Because if I dot product with this, you know, I'm going to get roughly what I would have expected. And then if I look at my ny axis here, well, okay, so that's kind of obviously incorrect there. Because this means that neither of my axes have any y component to them, which doesn't really make any sense to me. Why did that happen? What's going on there, right? If you look at what happens here, both of them have an x and no y component, right? But my x and y axes were in different places. You would think, at least I would think, that would give me a reasonable result there. So I have y-axis y, y-axis x, x-axis x, x-axis y. You know what? I bet I just can't copy y, x, y, x. God, you know? Usually it's the math that's wrong, but here today it's just copying the math into the code that's wrong, apparently. Let's try that again, folks. Okay, so now what are we looking at? Hey, look. So surprise, surprise, we did all the math right, apparently, but we just typed it in wrong. Okay, and so hopefully now you can see, and let me go ahead and build in release mode. But I wish I had just copied the math right. That would have worked the first time. It would have been great. But of course, then I had to stare at it for a while. So now you can see that our software renderer looks a lot closer to our regular renderer. In fact, it may look exactly like our actual renderer now. Let's go ahead and see if that's true, right? I'm going to go ahead and walk leftwise across the screen. So there we are. Perfect. All right. So that is that. You know, hopefully that... hopefully if you take these 3 days together, the day where we noticed the bug, the day where I wrote out all the matrix equations and showed why the bug was happening, and then today where we solved the equation and fixed the bug, you know, I hope that kind of gives you a good idea where... when people ask, you know, if you're a game programmer or whatever, do you need to know math, or what should I do about learning math? I hope that kind of shows just how important math kind of is. Like, trying to hack that to fix that bug, you'd never know, you would have no idea what was wrong, right? I mean, it would just be wrong, and you'd be like, I don't even know, you know, I have no idea what's right. But when you can go back to the original math and be like, I've got this transform, I'm trying to reverse it, I know that, you know, if I want to reverse the transform, I just solve the equation for the other term. And then you look at what actually happens to the math, even from first principles. You didn't need to know any tricks, right? I just solved those equations. You didn't even need to know what a determinant was, right? You just needed to know basic matrix multiplication, and everything else was solved with grade school algebra. And boom, you type in those 2 lines of code, and everything's fixed. Of course, you have to type them in right, which I didn't do. But if you can, assuming you can copy from your own math notebook into the code, it's perfect, right? And so that's just a really cool aspect of, and I think a good demonstration of why understanding math at a pretty fundamental level, at least the parts that we care about in game programming, is really pretty important. Because, you can fix bugs really easily. And, I didn't have to, remember, all I did was just invert that one matrix. I could have typed it into Mathematica, because I knew that's what I needed to do, and got the answer instantly. Way back when we first saw the bug, could have just done that, looked at it, and typed those lines in, right? So all the stuff we did, it wasn't like this huge, big ordeal. All that stuff I did was just me showing you so you would understand how it all worked. But the actual process is trivial. You just invert a 2x2 matrix. You can have Mathematica do that for you, or you can remember the determinant trick. It's right. So this would have been a 5-minute fix if I hadn't gone through and explained the entire thing from start to finish, right? So knowing that math and understanding all of that just allows you to immediately go, oh, right, okay, and the bug is fixed, right? Whereas if you didn't know it, you'd just forget it. I mean, you'd never fix it, right? You'd have to hack something in and hope you could maybe, monkey around with it or whatever. I guess that's basically it. I'm going to go ahead and go to the Q&A because I don't know if people have matrix Q&A questions here, but I guess I'd just say I don't want to get started on something in the last 5 minutes. So, if we don't have any more Qs, then we won't, but anyway. Miblo says, semi-off topic, but any chance you could describe a little more what you'd want of an algebraic Blackboard program? Yeah, certainly I could say pretty easily what I would want. So here's let me just describe the problem. And this is like why I don't like Mathematica. So here's what happens to me when I'm doing math, right? Is I'm actually not that bad at symbolic math. I'm not good. I've seen people who are good and they're really good. I'm not good. But I'm not that bad at that. I'm just bad at, I make mistakes when I'm, simple mistakes. I don't not know the right thing to do. I just make simple mistakes. But I know a bunch of stuff I can do to like massage things into the right forms that I want and all this sort of stuff. So I kind of know what I'm trying to do a lot of the times. But I have two choices, right? One choice is I can plug things into Mathematica, right? And what does that look like? Well, if I want to plug things into Mathematica, I got to type some stuff, and I don't remember the exact sense. It's been a long time since I used it, but I'm like, oh, okay, well, here's my matrix, Mr. Mathematica, right? And then I say like I've got my P, which is X, Y, or something like that, and then I type solve. And I don't remember their syntax for solve, but solve AP equals P prime or something. And I guess I have to put both of these in here. AP equals P prime, for P, right? Okay. So if I have a problem that's exactly like this kind that we just used, I think Mathematica is fine, right? You can put this in here, and what it will spit out to you is the scalar equation that solve this. So it will output something that's like a bunch of scalars here, like the scalar equations for the two things. So it'll be like, oh, U equals blah and V equals blah, which is the exact, this stuff that we just wrote on the Blackboard myself, right? It'll output this and that, okay? And that's where, like, most computer algebra stuff, like, not just math, I'm not picking on mathematics specifically, but computer algebra stuff in general, that's where it works okay, if that's all I want. But here's the problem. If I don't want it to drop down to scalar, all bets are off. So let's say that I was trying to work out some really big matrix equation, right? And there's, there's lots of stuff happening. So it's like, oh yeah, this was, A prime, AP cross, some other vector, AP cross B times, some other matrix here, inverted, and that was, added to some other thing, and blah, 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 right? When I'm going to program this stuff, I'm not going to do some giant matrix equation in scalar, right? And furthermore, I may not be looking for the solutions to these things. I may be looking for insights into how the problem works. So what I want to do is I want to actually move these terms around myself without ever dropping down to scalar, using rules that I know are okay. So I want to be able to say stuff like, oh, okay, trust me on this one, px cross b is equal to 0 or something like this, right? The 0 vector or something, right? I don't know. I'm just making stuff up like this. And other things like, oh, like A transpose B equals B transpose A, right? So I just tell it the things that I want to be true, right? And then I'm going to tell you what to do. So I'll say stuff like, oh, can you reduce this term in vector notation at all using the rules? Can you reduce it? And maybe it comes up with something. Or I'm going to say, hey, I want to multiply both sides by B, right? And so it'll do it and get rid of that term and put it here, right? And so that way I could work out the equations like I normally do on a piece of paper, but without ever worrying about making a mistake, right? So the computer doesn't let me make a mistake. But I never have to drop down into these crazy, huge scalar equations where I can't see the structure anymore and that are kind of useless to me at some level, right? So the more complicated matrix, vector, geometric algebra, whatever else stuff you do, the more useless Mathematica typically becomes because it just generates these huge scalar equations that don't tell you anything, right? You're like, well, that's okay if I just wanted to solve this one thing in scalar and type it in for an hour, right? But I don't want that. I want something that I can code using my own vector library, using the vector ops. Like I want to code this as a cross product. I don't want to have to look at Mathematica's crazy set of scalars and start trying to pull out where the cross products are, right? So just an augmented notebook thing where it doesn't have to be like handwriting. I'm happy to type in the equations, right? I just then want to be able to manipulate them knowing I never made a mistake by the rules that I input. The Sizik just says Q:, whoa. That is not a question, and I can't answer it. Error if. Semiratory, will there be more things like this that require math in further parts of the game? Although it was pretty basic, my math is a bit rusty. Well, I don't know. In 2D games, you get a little bit of a buy on the math. There's oftentimes less demand for the math, the harder core math in 2D. And that's not an accident. There's a lot of reasons for that. One of them is that typically when you jump to 3D, now you're doing a lot more real simulation, because since you have full 3D surfaces, you can do things that more closely approximate what happens in the real world. And so more math comes in there because it's more physics, basically. But the other reason is that 3 dimensions is more than 1 dimension harder than 2 dimensions. I know that's a very strange thing to say. But for example, a lot of things that are true in 2 dimensions aren't true in 3 dimensions. And it has nothing to do with the fact that you added 1 extra dimension, right? Because going from 1 dimension to 2 dimensions did not change this thing, but from 2 dimensions to 3 dimensions did, right? For example, rotations don't commute anymore in 3 dimensions, right? In 1 dimension, a rotation followed by another rotation, rotation A followed by rotation B, produces a rotation C, regardless of the order. So rotation B followed by A also is C. It doesn't matter what order I do the rotations, right? If I rotate this far that way, and then I rotate this far that way, I get the exact same thing whether I did this first or this first, right? Because it's all just a single scalar. It's just a theta of rotation, and no matter what I do, I always get the same, no matter what order I do the terms in. 3D, not true. 3D has winding, and so what ends up happening is, if you rotate one way and then rotate another way, you'll be in a different position than if you did those two same exact rotations in the opposite order, right? Tons of stuff like that is true in 3D. A bunch of things that, like, topology things break in 3D, things about fundamental geometry things just become not true in 3D anymore that were true in 2D. There's a bunch of stuff like computational geometry theorems that are just like, this is, in 2D, we know how to do it, we know how to do it in linear time, blah, 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 and they're like, in 3D, it's unsolvable, we've proved it's unsolvable, or stuff like that, right? And so there's just these really bad things that happen when you come to 3D. So when you stick in 2D, and that's why, what people often ask why I don't do 3D on Handmade Hero, there's so much more stuff that comes in 3D. I don't think anyone should ever write their first game in 3D. This is an awful idea. You should always have 2D first, because you get a bit of a buy on the math, a huge simplification on the asset pipeline, blah, 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 blah. And it's important to, like, get your fundamentals solid first, and then go do a 3D game after, when you can just focus on the new stuff you need for 3D without worrying about all the other stuff, like how to make an entity system and how to do memory management and how to... If you're trying to learn to be an engine programmer, don't try to learn it all at once. You'll just get discouraged, right? And so what I would say is, to answer your question about how much more math there'll probably be other stuff like this, certainly. It's not the only time that we do stuff like this. We've already done some stuff like this, and we'll probably do some more. But it is a lot lighter in a 2D game, right? It's not quite so much. It's not all the time. In a 3D game, you're doing this stuff kind of all the time. In a 2D game, it's less so. Brian Wag, do you consider math to be more of a tool to solve problems or more of a learned art to be mastered? I don't really know. I guess I don't really think about it in any particular way. Like, I usually just think of math as a really good repository of very smart people who have tried to solve problems before, and this is what they discovered, So I guess I think of it kind of like the tool to solve problems that you suggested, but a little bit more than just a tool, right? It's more like a way of looking at things and a way of leveraging the knowledge of people who came before you and what they were able to figure out, which is not really the same as just a tool, right? Because the tool to solve problems part obscures the fact that it's also the thing that helps you figure out what the problems even were to begin with. Like, I wouldn't even know that something was a transform or that it could be inverted as a way of thinking about texture mapping if I'd never had that basis, right? So I feel like I feel like it's I wouldn't just while I wouldn't necessarily say a learned art to be mastered, because that doesn't really mean much to me, I also wouldn't say that tool to solve problems covers it perhaps as adequately or as completely as how I actually view it. Googling what I believe you wanted turned up reducealgebra.com, automatic and user-controlled simplification of expressions and calculations. Ah, so someone maybe has written it now. Possibly? I don't know. Can't quite tell. Yeah, possibly. It's hard to tell from just looking at this, but that might be. I'll have to look at that. Symbolic, but I just wanted to note how your intuition of the transform seemed really important at finding the bug. Way more important than typing the correct formula. No, wait. I'm not sure exactly what that means, but I guess what I would say is I will state the thing that I think that is closest to that, which I definitely agree with and often try to point out, especially to people learning math, which is the important part of math is learning what all the math does and how, right? And the reason for that is because, like I said, all the actual solving, we could have actually just had Mathematica do that, right? You got to learn the finicky syntax in that, but it could have just produced the right answer for us, right? We just put in that thing, right? But knowing, and this is why I say hopefully this is kind of like what you were saying, because I feel this way too. Knowing what a transform was, that we were doing one, that inverting a transform involves more than just transposing the terms, blah, blah, blah. All of that is systemic mathematical knowledge that I know because I've studied the math, right? And there's really no substitute for that. You can't, at the moment, we don't have like artificial intelligence of this quality or anything, right? You can't, at the moment, type into Mathematica, please tell me why I'm getting this bug, right? And so that's why I think it's so important to know a lot of that math and have a broad math knowledge, is because a lot of times, if you don't understand all of these things and you don't have a way of slotting the problems you see into a mathematical framework, then it doesn't matter. You can't use math to help you if you don't know which math is involved, right? And so that, to me, is really the heart of the important part of a math education, is the broad understanding of all the different parts and how they work. And if you can't remember how to do them, that's okay. Just look it up at the time, right? But you need to remember that it did this thing, or how this thing does this, what it does, because otherwise you can't ever apply it. And I actually see this fairly frequently in programmers, actually, and it's a problem. There are people who have a much stronger math background, potentially, than I do, and I'll see them not know how to solve something that they totally should know how to solve. And the reason is because their math knowledge is too focused on how to actually work out the equations or something, but they never were able to actually build a big picture that allows them to do that slotting. That's like, oh, I've worked with this math enough, to use your phrase, intuition, to have an intuition for it. I know this is a transform. I know things I can do with the transform. I know things I can do with the dot product. I understand how they work. And maybe I forget how to do the math at the low level or something, but I can always look that up. But what I need to have quick access to and to have instant ability to read is that, am I working with one of these things? Is this important here? Could I solve this problem by applying this other thing? Might I, should I potentially try? And all of those things are really, really important. So I don't know if that's in the same spirit of what you were trying to say, but that is true. And that is really, especially when I look at how math is taught pre-college, at least, and sometimes, unfortunately, in college as well, but pre-college anyway. The problem is the amount of math that we learn in America, for example, up through high school. At least went to a decent high school. I mean, but so some people don't. But I mean, assuming you went to decent high school, the amount of math that I learned was actually pretty vast, but I couldn't do anything with it, right? And it wasn't until after I got out and was working on programming, and it was actually Chris Hecker, who I saw doing a lot of math to solve problems in programming, that I realized that, if I just go back and look at stuff I even already know, there's so much I can do with it, but they never taught me how to look at problems and figure out what math applied to those problems, right? And so gaining that framework in your brain of looking at problems through the lens of what math is important here is the very most important part of a math education, no question. And the actual doing of the solving is secondary, right? Because you'll never get a chance to solve a math problem by hand, even if you are going to solve it by hand, if you didn't know that was the problem you had, right? So that's totally true, and I think that's a very important thing to remember. Zillarisco, I actually just learned about determinants in linear algebra today. Do you think we will see them later on? Are determinants used often? I would probably echo the same thing I said before. Determinants are used pretty often, and they're used pretty often specifically because they have kind of a deep relationship to systems of vectors that you care about and want to do things with, such as invert and other things like that. However, we have limited need for those in 2D, so we probably won't be seeing them pop up like that frequently. But yes, they're a very common thing that gets used in linear algebra and its applications to 3D graphics certainly. Gasto5, do you get annoyed by some symbols meaning things in different things in different subcategories of math? No, I don't really get annoyed by that because, like I said, I'm not like a super strong symbolic math guy. And you can see that just when you watch me do equations on the blackboard. I'm constantly naming things the same thing. You know, like I'll be like, oh, okay, this is you, and this other thing over here is also you, and whatever. So it's like I just am not rigorous enough at those sorts of things to get annoyed at other people not being rigorous enough with those things. So, hey, yeah, these two branches of mathematics both use the same symbols, and it's kind of confusing. Okay, I make that same mistake all the time. I'm certainly not going to get annoyed. Might it be nice if it had been completely regularized the whole way? Sure, but, you know. Let me just double check to see if there are any more Q colons. Cubic said, what about 3D with an isometric view? The particular projection that you use for 3D, I'm assuming you're relating this back to the question of whether 3D is harder than 2D. Once you're in 3D, all of those things are true regardless of what the projection is used for your camera. The camera projection has nothing to do with it, right? It's just whether you decided to start trying to do full 3D things with full 3D surfaces and full 3D lighting and full 3D physics, right? So you can always cheese out on any of those that you want to and still maintain some level of pseudo 3D-ness in various ways and make things easier on yourself, right? But in general, you definitely have the case where the more actual 3D you want to be, the more strenuous the math will become. That's just because 3D is definitely more than one dimension harder than 2D, as I often say. What do you think of Khan Academy as a math learning resource? I haven't used it myself. Like I've never gone and said I want to learn, more differential equations. Let me go check Khan Academy. What I would say is I suspect that I probably wouldn't like it very much. And the reason for that is because I want to come at math from a programmer's perspective. And I don't think they generally do. Which is not a knock on them as a general math resource, but it is a bit of a knock on them as a programming resource, right? And so my preference would mostly be, a programmer-centric math learning resource would be what I would most want, because a lot of times, even though obviously math is math, what you emphasize and how you go about practicing and learning various aspects of it is definitely different depending on if you're someone who's, trying to learn to solve proofs for, the end goal versus someone who's trying to compute things as the end goal versus somebody who's trying to pass their college course as the end goal or whatever, right? So. And Cuber Caleb, yeah, a 2D game that's drawn in 3D is still a a 2D game for the most part, right? But you still, as soon as you even just do drawing in 3D, assuming that you're actually talking about drawing like meshes and stuff, you've got to start dealing with all of that additional math. Now, if you're talking about a 2D game that's drawn in 3D, but the 2D, everything's still sprites, you obviously get some by there as well. And everything you can collapse down from 3D to 2D saves you some math, right? And as we saw in Handmade Hero, you still have difficulties, but they tend to be of a different kind. Like our sorting thing, for example, is more hacky, like programmery stuff, and less rigorous math. Whereas the way we might handle depth stuff in 3D might have a lot more to do with math, right? LQ144, recognizing the kinds of things you're working with and the kind of problem you are working on is a fundamental skill. I'm not all that sure how to teach that directly, though, beyond doing something like what you are doing here and or repeated experience with solving problems. Well, yeah, I mean, my feeling on that is just that it's pretty obvious to me how you would teach math in schools if you cared about the actual useful part of math, right? And the way that would work is you would learn to do any particular thing in math once by hand, and you'd never really even probably be tested on it. You would just be able to use a computer algebra system or something to do that work for you as soon as you knew how to do it, right? And then all of your testing would always be on, here is a problem, and you need to figure out what math you're supposed to use to solve the problem, right? And then you can use the computer algebra system to solve it for you. And this is very, very different than the way these kinds of problems are given to you in school normally. Like when I went to school, the problems were always grouped into like the kind of problem they were. So it's like, we're going to have a test on UDU substitution. So you just know that every problem that you got is a problem on, integration, and it's an integration problem that's going to involve a UDU substitution. So it robs you of your fundamental practice of identifying that this is what's supposed to happen there, because all you're ever practicing is just the mechanical act of applying UDU substitution, which is something a computer can pretty much do flawlessly all the time. Like, it's really not the case that a human is necessary to do UDU substitution. Like, Mathematica can do that just fine, right? What Mathematica can't do is tell that what you were trying to do in this case is an integration in the first place, and that UDU substitution might be the way to go. I mean, Mathematica can sort of do that second part a little bit, right? So I really feel like, the way that sort of math should be taught is the students should never know what they are being tested on. That's like crucial. And then nobody should care whether they can actually do it by hand or not, because no one ever needs to do math by hand anymore. That's just not a thing. What we would care about is that they would know how to do it or where to look it up, how to do it, that they could get a computer to do it or write the computer program that does it, right? And save that for themselves, right? All of those things, great skills. Being able to actually do the equation by hand is completely irrelevant. I literally have no idea why you would ever need to know it. So it's exactly backwards. I think we have it completely backwards the way we're teaching it right now. We're teaching it as if we're trying to produce people from back in the day when they used to have rooms full of people solving equations because they didn't have computers to do it, right? And that's who we're making, and we don't need that person, right? That is just not a skill that we fundamentally need. But what we absolutely do need is people who look at problems and go, oh, I know what math could be applied here. I don't quite remember how to do it, but let me go look it up, right? And that's a great skill, because you can always go look up how to do the math if you know what the math is. But if you don't know, you'll never even know that you should be looking something up, right? You'll never even, it'll never cross your mind to go look up how to do integral arithmetic if you have no idea what integral arithmetic is and you don't know that the problem that you're faced with can be solved by integral arithmetic, right? So yeah. Anyway, but yeah, and as an aside, there is Handmade Hero. Actually, I think is a good math learning resource in a limited sense. In that way, that we are showing how to apply math to solve problems. But you know, most of Handmade Hero is programming, so it's not that good of a math learning because most of your time is not spent doing math. You could imagine a series that was done that was much more about let's not do a lot of programming, let's do a lot of problem solving with very simple programming to actually like implement just the minimum thing we need to like prove we solved the problem or whatever. That would be kind of a cool series, like math learning series that would be all about like finding places where the math is. And you know, like I said, we do that in Handmade Hero, and I think that's great. And I hope that exposes people to this kind of a thing. But you know, if you wanted to learn math real well, you would want a series that was just like all about that and all about the math. Whereas Handmade Hero is much more about the programming than the math. And we do the math when we need it, but we're not looking for excuses to do math every day, which is what you'd want, kind of that, you know, companion series, Handmade Math or something, right? So, all right, I'm gonna close down. Close it on down. Close it on down. Let's see here. Thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with a source code so you can follow along and experiment for yourself. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series. We have a schedule bot that tweets the schedule if you want to catch us live for the Q&As and just if you just want to hang out in the chat. And we also have a past episodes guide you can go to if you want to catch up on things we did before. That's about it for today. I will be back here tomorrow. I do not remember what time. I'll be completely honest with you. I think it's 5. Let's find out. Check that schedule bot. Yeah, it's 5 p.m. For the rest of the week, so 5 p.m. Pacific Daylight Time. Hope to see you here for that. Until then, have fun programming, and I'll see you guys on the internet. Take it easy, everyone.